Hello and welcome to the YouTube channel D Creations Resources. Today let us talk about the concept of electron diffraction. We all know that an electron is a subatomic particle with charge 1.6 into 10 raised to minus 19 coulomb and mass 9.1 into 10 raised to minus 31 kg. So we always think of it as a particle. Now, in the case of electron diffraction, we are able to see its wave nature. So, it's a phenomenon where a beam of electrons exhibits wave-like properties and it creates an interference pattern after interacting with a material, typically a crystalline material. And this is very important as a confirmation of the de Broglie hypothesis of wave-particle duality. In 1924, Louis de Broglie proposed that all matter, including electrons, has wave-like properties with a wavelength lambda, which is inversely proportional to its momentum. So, lambda is equal to h upon p, where p is momentum and h is Planck's constant. Now, when an electron beam passes through a crystalline material, the regularly arranged atoms of the crystal act like a three-dimensional diffraction grating. So, the electrons are scattered, but here they are in their wave nature. So, the scattered electron waves interfere with each other either constructively or destructively in specific directions as per the Bragg's law, n lambda is equal to 2d sin theta. And this results in a characteristic pattern of high intensity spots or concentric rings on a fluorescent screen or a detector. Now, electron diffraction primarily occurs due to elastic scattering, means the incident electrons do not lose kinetic energy during interactions with the atomic cores. The patterns that are obtained reveal the nature of the sample. So, if the sample is single crystalline, you see spot patterns, where the spots are arranged in a regular grid that represents the material's crystal orientation and symmetry. If the material is polycrystalline, then the patterns formed are ring patterns with many randomly oriented fine grains as the individual spots from each tiny crystal merge into continuous concentric rings. And of course, if the material is amorphous, then you get broad diffuse halo pattern. So, it indicates a lack of any regular repeating crystal structure. So, we are all aware of diffraction using X-rays. So, that is widely used to study the crystal structure. So, similarly, electron diffraction is also a powerful analytical technique. And usually it is with the transmission electron microscope or sometimes even with a scanning electron microscope. So, it is performed simultaneously and it's widely used for material characterization. So to determine the crystal structure, identifying the phase or orientation of materials, and this is especially useful for very small samples like nanoparticles and thin films due to the strong interaction of electrons with matter. So usually when TM images of nanoparticles, say for example gold nanoparticles, are obtained, electron diffraction pattern for that same area where the image is contained is also taken, so that you know that what is the composition of this particular image. So, suppose it's an image of a nanoparticle. If you are able to take its electron diffraction and it reveals that it is, say, face-centered cubic gold, then we know that this is a gold nanoparticle. So, if it is an electron diffraction experiment, you will have an electron gun which is going to basically release a beam of electrons, and then you will have a thin crystal target. Often graphite is used as a target. And you will have a fluorescent screen behind the crystal which is going to glow when electrons hit it. You will obtain a diffraction pattern on the screen, say in the form of rings. So, useful phenomenon and a technique. Thank you.